Hello and welcome to Chapter 8.3 from Stevens' Introduction to Statistics, the Think and Do book. In this section we're going to talk about hypothesis tests about a mean, and specifically we will assume that we do not know sigma, where sigma is the population standard deviation. Alright? And this is more than likely going to be the case. It's hard to believe that you would have a situation where you actually did know the population standard deviation. We're testing a claim about mu, where mu is the population mean, and sigma, the population standard deviation, is not known. So here's a preliminary example, and we will get to this example after we go through some of the basic setup. So Carl the farmer has started using organic fertilizer this year. The average weight of his tomatoes last year was 10.3. So that's last year, right? In a sample of 40 tomatoes from this year's crop, the mean weight is 9.8 ounces. So the sample from this year is a little below the 10.3 than last year's, with a standard deviation of 1.7. So that's the sample standard deviation, right? That's S. That's X bar. Right? Test the claim that the mean weight of all of this year's tomatoes is different from last year's mean. Test this claim at the 0.05 significance level. So basically we're saying, is 9.8 significantly different from 10.3? Right? Is there something unusual going on here, or is that maybe just a little bit of random variation that isn't all that important? Okay, so let's take a look at how to do this. We start off with our test statistic. There's the formula for the test statistic. It's basically a measurement of how many standard deviations above the population mean the sample mean is, in terms of standard deviations or standard errors. Okay, so X bar is the sample mean. Mu is the population mean assumed in the null hypothesis. S is the sample standard deviation. N is the sample size. So that gets us our test statistic. A few other things. We have alpha is the significance level. The degrees of freedom, which we'll need because we're going to be using the t-table. The thing to notice is that's a t, right? It's the t-score for the sample mean. So we're going to be using the t-table, which means we're going to need the degrees of freedom. And the degrees of freedom is always the sample size minus 1. Well, not always. In this chapter, it's sample size minus 1. And we'll have critical values of t, just like we used to have critical values of z, and we will denote them t sub alpha if there's one tail, and plus or minus t sub alpha over 2 if there's two tails. And basically, this t sub alpha, that's just a description. It means that alpha is the area in one tail. And what this one means, the t sub alpha over 2, it means that there's alpha over 2 in each tail. Okay. The process is similar to the process described in the last section, and is similar to the many times you'll see this throughout the book. You want to determine the null and alternate hypothesis. In this case, we're making a claim about a population mean, so we'll have a mu there equals 2 and some number. Mu sub 0 is a number here. So we're making a null hypothesis. The population mean equals some number. And then the alternate hypothesis depends on the claim. And you can get a right tail test, where mu is greater than that given value. Left tail test if mu is less than some given value. Or two tail test if I get a not equal to sign in the alternate hypothesis. Calculate the test statistic using equation 8.3 above. Do you reject or fail to reject the null hypothesis? There are two equivalent methods. We're going to be using this method, where we determine the critical values and the rejection regions, and reject the null hypothesis if the test statistic lies in the rejection region, just like the last chapter. The p-value method, we're going to sort of stay away from that for now, just because it's not good for us table users. If you have software, it's a perfectly good method, but getting the p-value from a t-distribution is just a tad bit tricky, and so we're going to avoid it because we have some other method that works just fine. We'll stick with this. and we'll be using the t-table, that number is wrong, that page. And then we make an understandable conclusion about the claim. Same 4 steps we did last chapter. Requirements: the sample observations should come from a simple random sample. And we should either have a population that is known to be normally distributed, and if not, we need a sample size greater than 30, or both is what I should put here. You need at least one of those 2 things to be true, or both of them. And notes on step 3, determining the critical value. So we're going to get, those pages are just wrong. This is the instructor version. Okay, so here's how you find this, the critical values, right? The critical values t sub alpha or t sub alpha over 2. So let's go to that. Oh, I'll switch to full screen mode. Notes on step 3. Let's go to my tables. The T table. Don't get dizzy, I'm scrolling along here. So we find our column. So last chapter we did confidence intervals. We're not looking at that at these now. Don't worry about those. Now we're looking at one-tailed alpha or two-tailed. So if you're doing a one-tailed test, you look along here for your significance level. Right? If you are doing a two-tailed test, you look along here for your significance level. And that determines your column. Right? And then the row is just the degree, whatever your degrees of freedom are, determines the row. So the idea is you want to look at one of these 2 rows here to determine which column you're in. And then the row is determined by the degrees of freedom. There's also something else worth noting. These are all positive, right? And remember, we can have negative or plus and negative. Sometimes we get 2. So you're always given a positive value. So suppose you have a right-tailed test. Right-tailed test. And you get z sub alpha equals 2.179, for example. That's great. But if you had a left-tailed test, then your critical value would not be a positive number. It would be the negative of this. It would be negative. So z sub alpha would be negative 2.179. If it was a two-tailed test, then z sub alpha over 2, you'd have 2 of them, would be plus or minus 2.179. So the table always gives you a positive value. You have to determine whether it's negative or the plus and minus based on whether it's a right-tailed, left-tailed, or two-tailed test. And that's what this says right here. Interpreting the critical value. If you're doing a right-tailed test, the critical value is the number in the table. If you're doing a left-tailed test, you take the negative value of what you found. And if you're doing a two-tailed test, you use the positive and negative values of the table value. The p-value method is not really good for us table users. You can get an approximation from table 3 by going to your, if you get your degrees of freedom, say your degrees of freedom is 9, and you have a test statistic of 2.95, you're in here somewhere. And so in a one-tailed test, that would be a p-value between 0.005 and 0.001. It's hard to do. You're sort of using the table in reverse. So I don't really like doing it, so I'm going to stop here. So that's the p-value method. If you have software, that's actually sometimes software, all it gives you is the p-value. It doesn't even give you the critical values because the p-value is sufficient to make your decisions. And all statistical software packages can give you p-values. They might not give you critical values. But stevenstats.com can show you whatever software you have available. Well, you might be able to find it at Stevenstat. I mean, we have SPSS, Minitab, Excel. The TI 82, 83, 84, all that stuff. Okay, so let's do that example about Carl the farmer, right? Last year, the average was 10.3. The average of all of his tomatoes last year is 10.3. So for this year, we have a sample of 40, and that sample mean is 9.8 with a standard deviation of 1.7. Test the claim that the mean weight of all of this year's tomatoes is different from last year. So what that's saying, if mu is the mean weight of all of this year's tomatoes, mean weight of, we'll say, all of this year's tomatoes, to emphasize that this is a population mean, then we're saying that that mean is different or not equal to last year's mean, which was 10.3. So this is important. It's not trivial, but we're saying mu, the mean from this year, is not equal to the mean from last year of 10.3. So once you get this straight, the null always gets the equal to sign, and the alternate supports the claim if it can, while being different than the null, and it can. So it gets the claim. The test statistic, it's right there. X bar minus mu. So look, X bar is the sample mean. That's 9.8. Mu comes from the null hypothesis. So it's 10.3. S comes from the problem is 1.7. That's the sample standard deviation. And N is the sample size, which is 40, making my degrees of freedom equal to 39. Okay. So when you plug all these things into the formula, you get a test statistic of negative 1.86. So we're going to make our conclusion to reject or fail to reject the null hypothesis. Let's look for our critical values. This is a two-tailed test. Two-tailed. And alpha, the significance level was what? 0.05. Degrees of freedom, 39. Two-tailed, 0.05. Degrees of freedom is 39. So this is a I'm going to erase all this stuff here. So it's a two-tailed test. So I'm looking at this row at the 0.05 significance level. So I'm in the middle column. My degrees of freedom is 39. And if you recall, middle column, 2.023. That easy. 2.023. But because this is a two-tailed test, I actually get the critical value and the negative version of it, right? So we get plus or minus 2.023 because it's a two-tailed test. And if you look at your test statistic, well, it's right here. Test statistic. That's the negative 1.86. That is not in the rejection region, so you fail to reject the null hypothesis. If you get software, you get a p-value of 0.074, and that is greater than the significance level. So again, you'd fail to reject. Right, so let's see what happens. Our alternate supports the claim, but we fail to reject the null hypothesis. So that's not so good. That's not good for our claim, right? So let's just let's see where we're going. We have the alternate hypothesis supported the claim, right? And we failed to reject it. So we say there's not enough data to support the claim that blah, blah, blah. So we go back here. There's not enough data to support the claim that the mean weight of all of this year's tomatoes is different from last year's tomatoes. Right? And we could have played this very similar game where we actually had a claim that they were equal, which would result in another type of two-tailed test. But basically what we're saying is 9.8 from a sample is not different enough from 10.3 to believe that the entire population mean is different than it was last year. It's not different enough. Right? Alteration. What we're going to do to this thing. suppose instead of claiming that they weren't the same, here we claim that the mean from this year is different from the mean last year. My big concern, they're actually small. My sample size is, or my sample mean is actually smaller than last year's mean. So what if instead of claiming that they weren't equal, what if I claimed that the mean from this year was less than the mean from last year? All right? So then this is my new claim, and my null hypothesis would be that mu equals 10.3, so that wouldn't change, but my alternate would be that mu is less than 10.3. What that's going to do is it changes from one tail to two tail, and it's specifically a left-tailed test. And so when you go and look inside your t-table for your critical value, it's now a one-tail test at the 0.05 significance level. So it's now here, which is second to last column, which means I have a critical value of 1.685 now. 1.685. And because it's a left-tailed test, it's negative 1.685, right? And now suddenly when you look at the test statistic, negative 1.86, that's over here in the rejection region. And I would reject the null hypothesis. So if you had changed your claim, suddenly you're rejecting the null hypothesis. If you use the p-value method, again, now I get a p-value that's smaller, 0.0352. That's now smaller than alpha, which is 0.05. And again, you reject. So I went from not rejecting the null hypothesis to rejecting it suddenly. And now we would say that the data supports the claim that the mean weight of all of the tomatoes from this year is less than the mean from last year. So in the previous example, we said there's not enough data to support the claim that the mean weight of this year's tomatoes is different from last year's. But just changing our claim, we come up and we say the data supports the claim that the mean weight of this year's is less than last year. So they seem to contradict each other. And the only reason they don't is because in this first conclusion, I'm not saying that they are different. Or I'm not saying that they're the same. I'm not finishing up this first problem and saying we're certain that the means are the same. We're just saying there's not enough data here to say that they're different. And here, when we change our claim, we say there actually is enough data. And the way this happens is when we set up, see, at a 0.05 two-tail, if you take a look at this, when you take 0.05 and split it in half into a two-tail test, these critical values are way out there. Whereas if you take the 0.05 and bunch it into one tail, it takes this, it's a left tail and test, it takes this critical value and brings it back here. So suddenly our test statistic was in the rejection region. So with a two-tail test, it's actually a little harder to reject the null hypothesis than with the same significance level on a one-tail test. Okay, so that's the sort of story of this alteration. Depending on how you set this thing up, you can get concluding statements that sound very different, especially if it's a close call. All right, so your turn 1, we're going to assume the body temperatures, and this is the one from way back in 8.1. We'll assume the body temperatures for healthy adults is a normally distributed random variable in a sample of 20. We can use that small sample because we're assuming that the parent population is normally distributed. In that sample of 20, the mean was 98.3. The standard deviation of that sample was 0.9. Use a 0.05 significance level to test the claim that the mean body temperature of all healthy adults is less than 98.6. So we're claiming that mu in this case is the mean temp for all healthy adults. And I'm claiming that it's less than 9.6. The null gets the equal to sign, the alternate gets the claim. My test statistic, x bar is 98.3, that's from my sample. Mu from the null hypothesis is 98.6. Sample standard deviation, square root of n, sample size 20. So I get negative 1.49. That's my test statistic. Conclusion about the null hypothesis and why. This is a left-tailed test, right? Left-tailed. So, to find my critical value, I have my degrees of freedom is 19, because my sample size is 20. My area in one tail is 0.05. 0.05 in one tail. So I'm looking here for 0.05. I go across, there it is. So I'm in the second to last column with 19 degrees of freedom. Brings me to 1.729. So that's my critical value, but this is a left-tailed test, so I have to remember that that's a negative 1.729. And then you look at your test statistic, negative 1.49. That is here somewhere, right? So that is not in the rejection region, and you fail to reject the null hypothesis. If you use software, you get a p-value of 0.0762, which is too big to reject. So again, you fail to reject the null hypothesis. Concluding statement, notice the alternate supports the claim, but we were unable to reject the null. So if you look at the null, we couldn't reject it. So we don't get to support our claim. Basically, we say there's not enough data to support our claim. There's not enough data to support the claim that the mean body temperature for all healthy adults is less than 98.6. Right. Why can you use the t-distribution despite such a small sample? Because we assumed the parent population was normally distributed. Remember, you need n is greater than 30 or normally distributed population. One or the other, or both. Would your conclusion change if the sample size was 100 instead of 20? Right, that sample was pretty small. So if I change my sample to size 100 and everything else was the same, basically this would be different. Instead of 20, it's 100, and negative 3.33 is the test statistic. And if you look at your critical value, it's negative 1.79. I would then be deep in the rejection region. So I'd reject the null hypothesis, and my conclusion would change to just the opposite. I would say the sample data supports the claim. Right. All right, so second, your turn. A report by the National Association of Colleges and Employers. The average starting salary for graduates in accounting is $48,993. And a sample of 50 graduates from IT, the mean starting salary is $52,089. Standard deviation of 13,500. The 0.01 significance level tests the claim that the mean starting salary for all IT grads is greater than that reported mean for accounting grads. So if this mu is the mean for all IT grads, I'm claiming that it's greater than the 48,993 for accounting. Greater than. Null gets the equal to sign. Alternate supports the claim because it can. Right? My test statistic. There's x bar, my sample mean. Mu from the null hypothesis. Sample standard deviation divided by the square root of n. So my test statistic is 1.62. Conclusion about the null hypothesis. I'm going to look for my critical values. This is a right tail test. That's good. That means I get to use the value in the table without taking the opposite or the plus and minus. It is at the 0.01 significance level, one tail 0.01, and the degrees of freedom is 49. Right. One tail 0.01. So if it's one tail, 0.01, I'm in this second column. right? So I have to go down to 49. Second column, oh good, it's not hard to get to at all. One tail, 0.01. 49 is my degrees of freedom, 2.405. That's my critical value. And if you look at my test statistic, that is over here somewhere. That is not in the rejection region. So we failed to reject the null hypothesis. If you use software, you get a p-value of 0.056, which again is bigger than alpha. And you fail to reject. So either way, using the table or with software, you fail to reject the null hypothesis. And now we got to look at a concluding statement. Again, our alternate hypothesis supports the claim, but we can't reject the null, so that's not good for our claim. Right? We don't have enough data to support the claim that the mean starting salary for all IT grads is greater than the average of that for accounting grads. Alteration, would your conclusion change if the significance level was 0.10 instead of 0.01? Well, let's see. What would be my critical value, right? If I was at 0.10 instead of 0.01, my critical value would be from this column, right? One tail, 0.10, it would be 1.299. So my critical value changes pretty dramatically, 1.299, right? So we get 1.299, and now if you look at your test statistic, which was 1.62, test stat was 1.62, that's actually in the rejection region, right? Because this is the rejection region. All right. Test statistic 1.62 is in the rejection region, so we would certainly wind up rejecting the null hypothesis, and then the data would support the claim. So at the 0.10, you're more willing to say, yes, the IT grad starting salary is higher than that for accounting. But if you're being a little more cautious at the 0.01 significance level for the first part, you don't say that. You sort of hold back and you say there's not enough data to make a call. All right, so that wraps up Chapter 8.3. And if you decide to do Chapter 8.4, which I don't usually do in class, I'll see you then, or you'll hear from me then. Or you can tune in for 8.4, but then after that we'll do the summary worksheet. All right, take care. Bye.